All right, let's continue. But before we start the next part, I want to do a clarification first. So I've double-checked the textbook and the implementation of the data cubes. So basically, here I used to say, okay, this for this time dimension, this hierarchy structure, particularly this part, is kind of invalid, or you have to choose either one of them, which this statement is incorrect. Okay, it's incorrect. So this whole hierarchy structure is valid. It's valid. This is because the relation between this all, year, quarter, month, week, and day, they're a partial order. So a partial order can also be used as a hierarchy structure, all right? And the reason behind this is that this kind of hierarchy structure, if you would like, it only represents a logical level view of the data cube. It does not directly related to the physical implementation. So for the put it in another way, I mean, you can understand it in such a way, saying that the data cube, when we actually store it on the disk, we always need to maintain the lowest level, right? The finest granularity, which is information about day, as the data cube you can see here. So basically, this generally, actually here, there are much. It's not only one cell; it's many cells. Okay, 31 cells perhaps. And when you want to execute a query like this, it will then find which part to do the aggregation, and then do the aggregation to get what you need. So it will all start from the lowest level. Then such kind of a hierarchy structure, it depends on whether you use a week in your query, or you use month or quarter in your query. So both way, the data cube can return what you need. Okay. So that's one thing. Another is that since we're talking about the implementation, the physical implementation of data cube, so there is actually a hidden dimension, which is the measures. In many data warehousing implementations, there is actually a virtual or hidden dimension here called measures. So these measures could include, for example, say the total amount of dollars of the sold items, or the number of sold items, or the cost, and so on and so forth. Then you can then this data cube can support different kind of queries, even with different kind of measures. Okay, and it does not need to create different data cubes for different measures. So these two things I just want to make a clarification here. Then let's continue where, okay. So the next part is about this the highest level all. So there's a good thing about of this data cube is that with this kind of hierarchy structure, we can actually expand the data cubes to support different kind of needs. For example, we use this two-dimension. We use this two-dimensional data cube as the example here. Say, all right, here we have different cities, right? And we have different products. Yeah, draw it here. Different products. Okay, now assume for the hierarchy, if we for the city, so assume that city is the lowest level, and there's only 2 levels. The next level is all. Then we can actually expand this data cube. Say no, not this dimension, but we'll do that dimension eventually. Okay, so we can expand the data cube. So this is for all cities, and then we can do the aggregation to sum up, which is to sum up the numbers here in this column. We can get the numbers here, okay, and so on and so forth. And we can do the similar things for product. Assume that similarly, I mean for product, product is the lowest level, and there are only 2 levels. Then we can expand the data cube within this direction and do the summation of this part to get the aggregation here, or the sum here. Okay. Then, for example, for this cell, it actually means say the total sales of product P3 within all the cities, across all the cities. Okay, and similarly, I mean, for example, this cell is the total sales in LA across the different, or all the products. Okay, all the products. And of course, you can draw this cell. It's like the total sales across all the cities and all the products. And all the products. So for 2D, two-dimensional example, it is kind of straightforward to draw it down and to get the meaning of each cell. So hopefully you would have an idea of what is this all mean, and especially this cell. It's kind of particular because it actually got takes all on both dimensions. All right. All right, but what if, because what if say the hierarchy structure is not that straightforward, say only 2 levels? What if, for example, for products we actually have categories, right? For cities we actually have a state as well. Let me find somewhere. Yeah, here is. So assume that this is the very detailed table or data cube. All right, so say these are the cities, so on and so forth, and these are the products. Okay, assume that this is the with the finest granularity. What we need, what we do is that we expand this cube on different dimensionalities. Okay. For example, we do the state first. Say if assume there are only 2 states, so New York City belongs to New York State, and this is California. So for this part, it has a higher granularity. So if we say this is city and this is state. Okay. And similarly, say this is a product, then we can expand the cube in this dimension as well. So assume that this is category, and we have say C1, C2. There are in total 2 categories. All right. Then, say for this cell, the cell here, it actually means the total sale of products belongs to category 2, category C2, that is sold in LA, right? And so on and so forth. Similarly, you can have the meaning of every cell within this light blue parts. And how about this part? How about the red part? Right? So the red part, for example, this cell actually means the total sales of product belongs to category C1 that is sold in the state New York. Right? And we can further expand it because we still have an or here, right? I think it's kind of straightforward. I don't need to explain the very detailed meaning for each cell, and I believe you've already get the idea, right? So this so basically this part, so this dark blue part is what we have, what we originally have from the transactions or from the facts, okay? And depends on different dimensions and their hierarchy structures, we can do the expansion. We can do the expansion on the data cube, and then it would be easy for us to answer questions involving aggregations of the data in the original table. So that's the good thing about data cube, where we can easily do the expansion, right? And similarly, I mean, now you probably could have a better understanding why I do that. I do this correction before, right? Think of if there is a dimension called time, what would you do to handle such kind of hierarchy structure, right? Because at first we only have the finest granularity, which is day, but it doesn't matter. It does not affect our expansion from day to month and day to weeks at the same time. Not exactly at the same time. I mean, it's like say, let's say this part is time, this dimension is time. So we can first do the expansion on weeks, right? This is week 1, week 2, so on and so forth. And then we can do the expansion then we can do the expansion on months as well. So this is January, this is February, and so on and so forth. Of course, I mean, the problem here is that when we come up to the higher level, we need to be careful. For example, if we consider year, we either aggregate all the numbers of all the weeks within a year, or we do the aggregation on top of these 4 quarters. But you can't take both of them in to do the summation, right? And similar for the level O as well. All right, so this is a 2D, two-dimensional case example. Let's look at a 3-dimension case. Yeah. So basically, the idea is totally the same as the 2-dimensional case. I mean, we only need to extend it from 2D to 3D, and perhaps to ND later in in real applications. Okay, so for 3D, I mean, it is similar. You just expand the cube within one dimension, and yeah, in this case, it expands within this product dimension. Then for a cell here, it actually means the sales of all products in New York City in because city is in this dimension, right? This is New York City, and here this is in January, right? And we probably don't take this new layer as a part of the cube here. We just take it as another cube, a new cube that is created based on this old one. What we do is we just stack it here for better visualization, right? So it's quite similar for the previous examples. So basically, how many new cubes have we created? It should be, so this is the original cube, and we have created 1, 2, 3, 4, 5, at least 5 cubes. Actually, it is more than that. We will touch that later. In fact, we actually created, say, 7 cubes, make it in total 8. And for this kind of cubes, we actually call them cuboid. So basically speaking, I mean, for each cuboid, it corresponds to a specific level in each dimension. For example, this blue cuboid, it corresponds to all in the product dimension, and city in the location dimension, and month in the time dimension. And you can create, you can easily create other, say, other cuboids. For example, the one corresponds to category, region, and all. You can do it flexibly. Okay. So the next question would be, I mean, each time, so the next question would be, how many cuboids do we have in total if we consider all the levels across all the dimensions, right? So assume that for the product, we have 3 different categories. And for date, we have different quarters. For country, we have different countries. So let's make this assumption to make things easier. I mean, easier for you to understand. Say for product, date, or country, for these 3 dimensions, they all have only 2 levels, right? So apart from the detailed products, it's all, right? And apart from quarters, it's all. And apart from countries, it's all. Okay. Then this cuboid is, they say, the original very detailed cuboids. And what we are going to do, we're going to expand it. Okay, expand this 3D cuboids. So how many new cuboids are we gonna generate? So from this figure, it's kind of easy to understand. I hopefully we have 1, 2, 3, 4, 5, 6 new cuboids, but actually we have 7. There is one hidden in the bottom layer. Okay, I try to draw it. but hopefully, I mean, you can understand what I'm doing. Okay, so this is because, okay, let's look at the green one here first. So for the green one, each cell, for example, this cell, it means the total annual sales because it takes an O on top of date, right? So it is the total annual sales of TV in USA. Then in general, each cell within this light green cuboid, it represents the total annual sales of a particular product in a particular country. And similarly, for this yellow one, this yellow cuboid, each cell represents, because we are doing an O on top of product, right? So each cell represents the total sales over all the products of a particular, in a particular country and in a particular quarter. Then for this blue hidden one, which is in the bottom layer, you can imagine, I mean, the aggregation is on top of countries, right? Because we have the aggregation on date, which is the green ones, the aggregation on product, which is the yellow ones, right? We must have an aggregate on country, which is this hidden one. So any cell in this within this hidden layer, this hidden is not hidden logically or hidden physically, it's hidden visually, right? You cannot see it in this kind of visualization way, but it is actually there. So basically, a cell represents the total sales of a particular product in a particular quarter across all the countries, right? So these three cuboids are kind of larger than the rest ones. They're smaller than the original ones, but they're larger than the rest ones because they only do the aggregation on one dimension. Now, what is the next level? The next level is, what if we do this kind of aggregation on 2 dimensions? Right? So in total, we have 3 dimensions, right? So if we take O on both product and date, we will have this gray cuboids, okay? So for example, this cell actually means the total annual sales of in USA in this whole year, right? And similarly, for this cuboids, we're doing aggregation on product and country. Let me see if I can find an easier way for you to remember or understand this. Oh yes. So basically, as you can see, I mean, for this cuboid, the only dimension that it has multiple cells. For example, on this dimension, it only has 1 cell, right? And on this dimension, if you can imagine, it only has 1 cell as well. But in this dimension, it actually has more than 1. All right, and this dimension is the dimension of date. Okay, because the line here is parallel to the line represents to the line represents date. Okay. Then it means that the aggregation is on the other two dimensions, but not date. Right? So each cell means the total sales of the total sales of all the products across all the country within this particular quarter. Right? And similarly, for this green one, let's see, this dimension is product because it is parallel to the direction of product. Sorry, this dimension is country. It's my bad. This red dimension is country because it is parallel to the direction of country. And if we use another color, this dimension is product, right? And this dimension sorry, not this one. Yeah, this dimension is actually date, right? Because it is parallel to the direction of date. So we see that it has one cell on the country dimension, one cell on date dimension. So it is the total annual sales across all the country of a particular product because it has multiple dimensions, multiple cells on the dimension of product. Right? So these three cuboids are what we have if we do the aggregation on 2 dimensions. And this left us the last one, which is this one. So this one, it has only one cell, and apparently it represents O and O. So it does the aggregation across all the dimensions, across all the dimensions. All right. So far we have discussed an example, or say a special case. All right. The next thing we need to do is to generalize what we have been discussing. Okay. So in order to generalize that, we need to have a more abstract understanding of this. All right. So basically, for any cuboid, for example, here we have in total 8 cuboid. So for any cuboid, if we take a cell in it, the cell should represent the measure of, say, different dimensions on different dimensions with different levels. No, this is too abstract. Let me see. For example, the cell here, or in this white cuboid, it actually means the cell, right? The total cell of some product in some country within some date, right? Because here the product, country, and the date are the level name. Note, it is not the dimension name. For example, the dimension name of time of date should be time, of country should be location, of product should be I don't know, just say it's prod or whatever. Okay. these are the dimension name. But what we are talking about is the level name. It's the level name. Okay. So, for example, the cube in this yellow cuboid, a cell represents what? Yeah, it represents the total sales of some date, right, in some country across all the product. See here, all is also a level name. It's also a level name. Now, no matter to say this dark blue one, right? It is the total sales of in all countries in the whole year for all the products, right? So 3 all, but they are all level names. Now, can we do this kind of assumption, saying, okay, give you any say if we have let me see, if we have n dimensions. First of all, if we have n dimensions, in this case we have 3 dimensions, but we could have more dimensions, right? If we have n dimensions, and if for each dimension I give you a specific level, you should be able to create a cuboid corresponds to these level names across n dimensions. This example is kind of not that good, because we assume, say, all of these 3 dimensions only have 2 levels. But assume that you can imagine if, for example, between country and all, we actually have a region or whatever, right? Then can we build a cuboid for, say, for different products in different dates across all the regions? No, that's meaningless. Sorry. Can we create a cuboid for different regions of different date for all the products, right? Or can we create a cuboid for different regions for different dates for different product? Actually, we can do that as well, right? It is just similar to what we have doing, or what we have do here, if you would like, right? This is the say this corresponds to the white cuboid, the very detailed one, the original one, right? These are the all. These are the cuboid that involves at least one dimension is all, right? Excuse me. Yeah. So that's why I mean, previously I said here this is one cuboid because it is all and particular for a particular product. It's all and product, right? This one is all and category. This one is all and all. Similarly, this is all and state. This is all and city. Now, what about this one? It is category and state, right? And of course, category, product and state, category and city. So in total, we have 9 different cuboids. Okay, and for each one of them, for example, here, this cell just represents the total sale of the products in C2, right? Across the California state, right? And you can do the others by yourself as well, all right? So the idea here is that by doing so, we can actually compute how many cuboids are we going to create. How many different, or say how many different cuboids can we have at most, if you like. All right. So here we first define this n-dimensional cube. Okay, this n-dimensional cube. So the let me see. The definition of this n-dimensional cube is that, first of all, say if there are totally n dimensions in this data data warehouse. When we model this data warehouse, or we model the data, there are in total n dimensions, or say x dimensions. Then the base cuboid, which is also the x dimension cuboid, is the lowest. Well, in this figure, it's kind of the highest, but if you see the direction of the arrow, it is actually the lowest level of this lattice structure. But anyway, I mean, we call it base cuboid. It is just like the white cuboid here, right? Because for each dimension, we're not doing any O aggregation, okay? But if we do the O aggregation on top of, for example, here should be country. Here should be country. Right. So if we do the aggregation or aggregation on top of country, we would have a cuboid like this. Okay, because this cuboid actually represents the total sale, for example, across different products and different quarters, and so on and so forth. Here should be a country rather than a store. Okay. And similarly, I mean, this is the cuboid across different quarters and different countries, right? So the O aggregation is on top of product, right? Here the org aggregate, this one, the org aggregation is on top of quarter, so it's across different product and different countries, so on and so forth. So basically here we have we call them two-dimensional cuboid because they kind of have the degree of freedom of 2, if you would like, or if you would like to use other ways to describe it. Because we have fixed one dimension to all, right? You have the freedom to choose, say the values on other 2 dimensions, right? So it's a two-dimensional cuboid. Okay. So similarly, for one-dimensional cuboid, you only have the freedom to choose the value on 1 dimension. For example, here you can choose different countries, here you choose different products, and here you choose different quarters. Right? But all the other 2 dimensions are aggregated to all. Right? Therefore, for this 0-dimension cuboid, apparently it's O and O and O. So basically, you have no freedom to choose any values on any dimensions. Okay. So an n-dimensional cube can be represented as D1, D2 to DD. Let me see. Where Di is the set of allowed values on the ith dimension. So here should be Dn, right? For example, the 2-dimensional cuboid, right, can be represented as D1 and D2. So D1 is the set of allowed values on, if we take this as the example, on product, and D2 is the set of allowed values on quarter. Right. So say if DI equals to LI, which represents a particular level, then DI equals to all the descendant dimension values of LI. This is kind of easy to understand. All can be omitted and hence reduces the effective dimensionality. Okay. Then a complete cube of d dimensions, consists of this much cuboids, right? So it's so where here the Ni is the number of levels, excluding all, on the ith dimension, right? And they collectively form a lattice. So it is we have from the example before, it is easy to understand here. So basically, for each cuboid, it is just to decide like the measure with corresponds to different levels across different dimensions, right? So this Ni plus 1 actually, because here Ni excluding all, therefore Ni plus 1 actually including all, right? Because all is the top level. So basically, for example, we have 3 dimensions, right? The first one have 3, the second one have 4, the third one have 3 different levels, including all. Okay, let's do it excluding all as well. So yeah, all right. Then every time when you build a cuboid, or say any cuboid, must correspond to either one of these 4, and either one of these 5, and either one of these 4 levels across these dimensions. So this is a classic combinatorial problem where the total number of possible combinations are apparently 4 times 5 times 4, right? Which is 80 in this case. Okay. Well, it is best to finish here because we just finished, say, one part, and the next part would be, say, the operations, and that is a fairly big part, cannot be finished within 5 or 10 minutes. But okay, let me try to pack up the takeaway messages for today's lecture. And if we still have time, I probably just start a little bit on the next topic. All right. So today we're discussing we have discussed the multi-dimensional model. Okay. So the most important thing you need to know is that for a multi-dimensional model, which is a data cube, you need to know what are the facts and hierarchies. For facts, what are the measures and dimensions? And what is the relationship between facts and transactions? All right. So basically, transactions are the facts. That's why I say if the cell is empty, there's no transactions there, and there is no facts. Okay. For transactions, we need to determine which measure do we have. These measures, some of them can directly obtained. Some of them are hidden or explicitly obtained. We need to do some mathematics, right? Dimensions is the context of the measure. Always use an example to help you memorize all these things, all right? And also the hierarchies. Always use the example. For example, here, the measure is the dollars sold, right? The dimensions are, say, store or product or time. such kind of things, right? But the different thing, or what makes a data cube different from traditional relational database is that, okay, this kind of data cube, the row and the column, or if for higher first of all, I mean, the row and the column, even for a 2D cube, can be swapped, where the relational database you cannot, and it can be easily extended the definition or the concept to a higher dimensional space, right? And then within this hierarchy, there is a very important. Within this hierarchy, we actually this kind of relationship between different levels actually help us to build different cuboid. Okay, and O is considered to be a special level, right? And with all these levels and O, we can actually have this kind of n-dimensional cube, as well as we know how many cuboids do we have. All right. So basically, it's all about cubes. So we need to know what are the cubes, right? What is the semantic meaning of the cell in a cube? Right? What are the measures, the dimensions, the hierarchies? How many cuboids would be in an n-dimensional cube? Right? So that's pretty much all for today. And to start a little bit on next part, which is the operations of data cube. Right. So there's only one constraint for the operations on the data cube, is all these operations should be closed. It is just like in relational database. Those operations in those SQL operations are closed as well. I mean, even if you select only one row, it will return you a table, right? The input and the output of a SQL query, they are both tables, right? So in data cube, it is the similar. I mean, both of the input and the output of an operation should be a cube, should be a data cube. Okay, why? Because only in this way they can be composed. Right? We can take the result from another operation as an input of a new operation. Okay, so there are mainly 4 different kind of operations. Right? There are roll up, drill down, right? Slice and dice, and pivoting. Okay, we will discuss the details about these 4 operations in next week's lecture. Okay, so that's pretty much for today. I see you next week.